In the last video, we talked about functions with vertical asymptotes. These occur when the output of the function blows up as the inputs approach a finite value. In contrast, you might also wonder what happens when the input is allowed to blow up instead. That is, what happens to the function as x goes to infinity, or minus infinity. Such limits are about the end behavior of the function, and if they exist, they're called horizontal asymptotes. For example, consider the function f of x equals 1 over x all plus 2, which is obtained from the hyperbola 1 over x by a shift of 2 units in the vertical direction. From the graph, it's clear that as the input x grows very large, the values of f of x are tending to 2. And from the other direction, as x grows very negative, the values of f of x are still tending to 2, but now from below. In this situation, the line y equals 2 describes a horizontal asymptote of f because the graph of f approaches this line either as x becomes very positive or as x becomes very negative. Some functions actually have two horizontal asymptotes. For example, consider the function f of x equals arctan of x. This function tends to pi over 2 as x goes to infinity, but as x goes to minus infinity, it tends to minus pi over 2. This means that the two lines y equals pi over 2 and y equals minus pi over 2 are both horizontal asymptotes for this function. This end behavior of arctan can be seen from the corresponding limits of tangent. As x goes to plus or minus pi over 2, tangent of x tends to plus or minus infinity. Alternatively, the asymptotes of arctangent can be seen from its graph, which is obtained from the graph of tangent by reflecting about the line y equals x. Some functions have no horizontal asymptotes, such as the function f of x equals x to the third, whose graph doesn't approach any horizontal line. In the case where there is a horizontal asymptote, however, algebraic manipulation can be useful in finding it. For example, consider this rational function and consider its limit as x grows very large. From first glance, it's not so clear what the limit should be because both the numerator and the denominator grow very large, so it's hard to know what would happen to their quotient in the limit. But if we divide both the numerator and the denominator by the highest power of x, in this case x to the fourth, we find that the limit is equivalent to the limit of a new quotient, where both the numerator and the denominator are tending to finite numbers. In this case, the numerator is tending to 40, whereas the denominator is tending to 10. What this means is that the quotient is tending to the value of 40 over 10, which is 4. This type of algebraic manipulation can work in more complicated situations too. For example, this quotient involves a square root in the denominator, making it a bit more unwieldy. But the same principle of dividing both the numerator and the denominator by the highest power of x will still apply. Now, we just had to remember that the denominator has a square root, so when we bring our division of x to the third inside of it, the x to the third becomes an x to the sixth. At this point, we recognize both the numerator and the denominator tend to finite numbers in the limit, the numerator to 10 and the denominator to the square root of 25, which is 5. In total then, the limit is 10 over 5, which is 2. Other algebraic techniques, such as multiplying by conjugates, can be useful too when investigating horizontal asymptotes. For example, suppose we want to investigate the end behavior of this expression, which is the difference of x minus the square root of x squared plus 2. Trying to take x very large in each piece separately doesn't work very well, because we get something like infinity minus infinity, which isn't a well-defined quantity. Instead, let's try the trick of rationalizing the numerator to rewrite the difference as a quotient. After some algebra, we realize we're in a situation like before, where dividing by the highest power of x could be useful. So we do so, and we're left with a limit which we can easily compute. The numerator tends to minus 1, whereas the denominator tends to 1 plus the square root of 1, which is 2. So the limit in question is therefore minus 1/2, a limit which isn't so obvious from the start. One way of thinking about this example is that it shows in some way that infinity minus infinity equals minus 1/2, but there's actually nothing too special about the number minus 1/2. In fact, it's possible to show that given any number a, it's always possible to write a as a limit in the form of infinity minus infinity. In other words, infinity minus infinity is not a very good expression at all because it could literally denote any number. For this reason, it's always good to be extra careful when dealing with expressions that involve infinity, because infinity is not such a well-defined quantity after all.